Hello, everyone. Um, I am not feeling my best right now, so I'm not going to be able to make it to class for the lecture on Monday, October 30th. So I'm going to do a video lecture here instead. So we're finishing homework 10 today, and then homework 10 will be due on Sunday. That's November 5th at midnight. But keep in mind that we are going to start homework 11 on Wednesday and continue with homework 11 on Friday as well. So we're going to be halfway through homework 11 by the time this is due. And it's going to feel like a really long time since we've talked about this if you wait until Sunday to start it. So um, I would really strongly encourage you to start homework 10 as soon as you possibly can. It's going to ease things for everyone. So that's my stuff and things. So let's go ahead and work through the rest of homework 10 material. So last week on Wednesday and Friday, we did graphing rational functions. Um, and so we've got a couple of other graphing things that I kind of want to go through, and then we're going to do solving rational inequalities. Okay, I want to start with number 2 here because I think that's going to remind us of where everything comes from, and it's going to make number 1 a lot easier if we start with one of these guys. Okay, so we need to choose the correct graph of the function f of x equals 2x over x squared minus 9. And we've got a line up here of graphs. So to start this, we're going to start with, if we were graphing this by hand, we are going to identify our horizontal asymptotes, our vertical asymptotes, our x-intercepts, and what am I missing? Horizontals and holes. That's the other thing. There we go. So we're going to start where we always start with rationals, and we're going to factor everything. The top is already factored. That's just 2x. And then x squared minus 9 is a difference of squares. So this factors into x plus 3, x minus 3. Okay, and then we're going to use this factored version to identify holes, x-intercepts, and vertical asymptotes. So there's no canceling here, so there's no holes, and I've got no simplifying to do. And then basically, once we have identified holes and canceled, anything left on top tells us our x-intercepts, and anything left on the bottom tells us our vertical asymptotes. So let's find our, I guess, x-intercepts first. So our x-intercepts here are going to be where the numerator 2x is equal to 0. I have an x in here so I can solve this. Dividing both sides by 2 tells me that I have an x-intercept at x equals 0. So that means my x-intercept is the point 0, 0. Because x equals 0, we just solved that, and y equals 0 at x-intercepts. And then we'll find our vertical asymptotes next. That's where the denominator equals 0. So if the denominator equals 0, that means either x plus 3 equals 0 or x minus 3 equals 0. And so that means I have vertical asymptotes, at x equals negative 3, and I have a vertical asymptote at x equals positive 3. So I've got 2 vertical asymptotes here. Okay, and then the last thing that we need to identify here is horizontal asymptotes to put this on a graph. Horizontal asymptotes, this comes from end behavior, and end behavior comes from leading terms. So we'll start by identifying our end behavior fraction. We'll come here for this one, just because it's already, the bottom's already multiplied out for us. We can see what our leading term on the bottom would be a little bit easier there. So we're going to take leading term on top, which is 2x, and our leading term on the bottom, which is x squared. And we're going to simplify this, and I'm going to get 2 over x. 1x cancels 1x on the bottom. And then as x goes to infinity, because again, we're looking at end behavior, and this is our leading term for the whole fraction, essentially. So as x goes to infinity, 2 over x goes to 0, because when you take 2 and you divide by bigger and bigger and bigger numbers, you're dividing 2 into more and more and more pieces, and your pieces get teeny tiny and head toward 0. So that means I have a horizontal asymptote at y equals 0. Okay, so now that we have identified all of our stuff and things, now we just have to identify the graph that contains all of these stuff and things. Okay, so I like to start with my asymptotes here. So we've got vertical asymptotes at x equals -3 and x equals +3. A looks like we've got vertical asymptotes at -1 and -4, so that's not it. Graph B is still a contender that has vertical asymptotes at 3 and -3. Graph C has the correct vertical asymptotes, as does graph D. But E, this has that -1 and -4, which isn't right. And graph F has -1 and -4 again. So those are the wrong vertical asymptotes. So we're just kind of doing elimination right now. Okay, and then we have to have a horizontal asymptote at y equals 0. Graph B has one. Graph C, this has a horizontal asymptote at y equals 3. That's not right. And then graph D has a horizontal asymptote at y equals 0. So with vertical and horizontal asymptotes, both D and B are options. So now let's go to our x-intercept here. I know that the graph needs to go through the point 0, 0. We need to touch or cross the x-axis there. Graph B has an x-intercept at 0, 0, so that is good. And graph D does not go through this point. So I know it's not graph D. Graph B is the correct graph of this thing. So just kind of a heads up, sometimes you will have two graphs that have the same x-intercept, vertical asymptotes, and horizontal asymptotes. For instance, if we had had a graph that looks a lot like the one that we have now with the same asymptotes, but instead of going up to down, left to right, sometimes you'll have a graph that does this. And so in this case, this graph would have the correct vertical asymptotes, horizontal asymptotes, and even this x-intercept here in the middle. So if you had two graphs, graph B and this graph left, how would you tell which one was correct if they had the correct intercepts and asymptotes? Well, the answer there is you're going to pick one extra point. So you would pick, I don't know, for us, let's go x equals 1. And I would plug it into my function. And y is going to be 2 times 1 over 1 squared minus 9, which is 2 divided by -8. That's -1/4. So that means the point 1, -1/4 has to be on my graph. And notice here when x equals 1, this graph is below the x-axis. That looks believable to me to have a point at the ordered pair 1, -1/4. But if I come to this one down here, which was my other option, at 1, which is right here, the y value is above the x-axis, which is not right, and I would be able to get rid of that one. So I just wanted to mention there, sometimes you'll need to plug in an additional point if you've got two graphs that are still contenders, even after you find all of this stuff. Okay, so now that we have kind of run through this again and your brain remembers how to find all of these things, let's come back to number one. I want to write the equation of a rational function that has x-intercepts at 0, 0 and negative 1, 0. So that means I have x-intercepts at x equals 0 and x equals negative 1. I need to have a whole at x equals 3, and I need to have a vertical asymptote at x equals 5. How would we do this? Well, we have to start thinking about where these things come from. So I know this is going to be a rational function. So I know that my function is going to be a fraction with variables in it. So I'm going to make a fraction bar. Let's start with a whole because I think this is the one that's easiest for most people's brains to start with. Where do wholes come from? Wholes come from canceling, right? And so because I have a whole at x equals 3, that means I had to have a very specific factor that canceled on both the top and bottom. Specifically, to have a whole at x equals 3, the factor that would create that is the factor x minus 3. And because it's a whole, that factor needed to cancel. So x minus 3 has to appear on both the top and bottom here to create a whole at x equals 3. Okay, so let's move on to the vertical asymptote then. If I have a vertical asymptote at x equals 5, what needs to happen to my function? Well, vertical asymptotes come from the denominator, right? So I need to put something in my denominator here to create that asymptote. What is it that I need to put down there? Well, to have a vertical asymptote at x equals 5, the factor that would create that is x minus 5. So I need to have an x minus 5 here on the bottom to create that vertical asymptote. And then how about our x-intercepts? These guys come from the top of my function. So I know I need to add something up here to the top of my function to create x equals negative 1 as an asymptote. I'm going to need x plus 1 to appear up here. That would create an x-intercept at x equals negative 1. And then I also need an x-intercept at x equals 0, which means I need a factor of x minus 0, or just x, right? And so here's my function. F of x is equal to x minus 3 times x plus 1 all over x, or times x, sorry, all over x minus 3 times x minus 5. We've got the canceling, our vertical asymptote, and our x-intercepts. And just leave it factored. I don't want you to multiply any of that out. I'm just looking for where things are coming from. All right. So that kind of wraps up a lot of the graphing stuff. But there's one more little thing where you'll be given a graph of a rational function, and we're going to have to identify some things about it. So you're given this graph right here. And so we'll start with identify the vertical asymptotes. Okay, so the vertical asymptotes are those vertical dotted lines. So our vertical asymptote is this guy right here. The equation of that vertical asymptote is, it's vertical, so it means it's x equals, and this goes through the point, or this goes through the x value, x equals 5. So that's the equation of my vertical asymptote in this graph. Now we want to identify the horizontal asymptote. Does this have one? Yes, it's even dotted in for us right here. Our graph approaches this line on both sides, and it's a horizontal asymptote, which means it is a horizontal line and has the equation y equals. And this horizontal line is at y equals 0. So that is our horizontal asymptote here. Okay, how do we identify x-intercepts from the graph? Well, x-intercepts are where we across the x-axis. So x-axis is here. I'm looking for any place my function touches or crosses this line, but it doesn't touch or cross that line anywhere. So that means this thing has no x-intercepts. Sometimes you will have them, sometimes you won't, and that's really messy, sorry. No x-intercepts, a little bit better. And then how about our y-intercepts? The y-intercepts are where our graph crosses the y-axis here. And notice the only place that I cross the y-axis is right here, and that's at y equals -1, or you can write that as an ordered pair. X is going to be 0 because it's a y-intercept, and y is -1. So you can write that either way. Okay, and then lastly, these are the big two that I wanted to make sure that we went over because it's been a while since we've done this with graphs. We want to do the domain and the range of this thing. So, sorry. All right, domain. Remind me again what domain is. Domain is what x values have a partner to go with it, what x values have a y that they're linked to. And so we can really kind of go section by section here. If we start with this section, this covers all of the x values in here, right? And this has an arrow on it, so I'm going to continue that way forever. And then this part keeps going and keeps going and keeps going. And we're approaching this vertical asymptote, so we're going to get closer and closer and closer and closer, but never actually get there. So this thing can't have a y value with it because that's what a vertical asymptote does. It says you can't put a y value here because your brain's going to explode. And so this x equals 5, that can't be in my domain. That's what a vertical asymptote is. Okay, and then let's look at this section. So this section kind of does the same thing. It covers all these x values in here, and I have an arrow, so this is going to continue on that way forever. And if we follow it back the other way, we get closer and closer and closer to this vertical asymptote. So we're going to keep going and going and going closer and closer and closer and closer, but we're never actually going to get there. So notice all of our x values are covered except for x equals 5, which means our domain is -infinity to 5, union 5 to infinity. It's everything except 5. Okay. Hopefully that makes sense. And then now we're looking at the range. Let me try to switch colors here. So the range is the opposite. What y values have an x value that go with them. So now we'll kind of look at our pieces here. This piece right here covers the y values in here. It covers all of these guys. The arrow will continue on down here forever and keep covering those guys. And then here, my y values are going to be, as this comes up, my y values are going to be covered and covered and covered. And I'm going to get closer and closer and closer to the x-axis, but never actually touch it. So that means I'm going to cover everything below y equals 0. And then if I look at this section as well, this covers exactly the same stuff all the way back up to y equals 0, but not quite getting there, which means my range is going to be -infinity up to 0. And I'm not going to include either of those. And again, make sure you put the small one on the left, the big one on the right. That -infinity has to go on the left. I'm going to continue to be really picky about this on tests and quizzes, and I'm going to keep taking points off for this because I need you to get to the point where you always put the small one on the left, the big one on the right. All right, so that's domain and range from a rational function graph. And that's going to be our last graphing topic here. And then we're going to switch gears a little bit. And the last thing that we're going to cover is solving rational inequalities. Now, we've done several different kinds of inequalities up to this point, and basically, since we've done linear inequalities, everything after linear inequalities is going to be solved the same way. With quadratic and polynomial inequalities, you solved the equality, you put those solutions on a number line, you tested values in each section of the graph, and then you wrote your solution, including the pieces that work. We're going to be doing exactly the same thing with rational inequalities. We're going to follow our inequality process, but we have to be really careful about the setup before we put everything on a number line and test values, but we're still going to do that. So with rational inequalities, the first thing that I need you to do is get a 0 on one side of your equation. So you're going to move everything that you're given to one side of the equation, subtract everything over to the other side so that you have a 0 on one side of your equation. You must do that first, establish your 0. And then um, after you move everything to one side, if you have more than one fraction on that side, I need you to combine fractions by getting a common denominator. Your goal is to have one fraction and one fraction only on the side that isn't 0. So we want one fraction being equal to 0. You must get that set up before you go any further. One fraction on one side, a 0 on the other. And again, if you're not given that setup, subtract everything to one side and then combine those fractions on that side by getting a common denominator. And then you'll have one fraction on one side, a 0 on the other. And then once you are in that magical configuration, now is when we can start solving this. I want you to factor everything in both the numerator and denominator. And if you have any canceling, go ahead and do it. We actually aren't going to worry about holes or anything like that. In our case, if there's a hole, cancel it and simplify. We don't even need to take note of the holes. They are not going to affect inequalities. So go ahead and factor everything and simplify it. Cancel if you can. And then normally this is where we set our equation equal to 0 after we factor um, and then test values. This time we have both a numerator and a denominator. We are going to set both the numerator and the denominator equal to 0. You set them both equal to 0. So you set the top equal to 0, you set the bottom equal to 0, and then you take the solutions from both of those equations and put them on your number line. And then you chop your number line up at each of those values, test values in each of your piece, and to test them, you can plug them into your simplified rational inequality. You can also use your original, but if you had any canceling, it just generally makes your life easier to put it into the simplified one. So that's kind of a choose your own adventure. So you can really plug them into any inequality that you have and you'll be just fine. And then I want you to write your solution just like normal with interval notation and include all of the pieces that work. Okay, so let's do this. Number 1, x minus 1 over x plus 7 is greater than 0. Okay, so again, we need to get our magical setup before we start solving this. I need one fraction on one side and a 0 on the other. Notice I have a 0 here already, and so I don't need to move anything over. That makes me very happy. And on the other side, I have a single fraction over here, which means I don't have anything to combine. I am set up in my magical setup, and I can go ahead and start factoring and simplifying. So I'm going to look to factor and simplify everything in this one fraction over here. But I don't have anything to factor. There's nothing, no factoring to do. And so there's no simplifying to do either. I don't have any canceling. So from here, I'm going to set both the numerator and the denominator equal to 0. So when I set the top equal to 0, I get x minus 1 equals 0, which means x equals 1. And then when I set the bottom equal to 0, I get x plus 7 equals 0, which means x equals negative 7. I'm going to take both of these and put them on my number line to chop it up into pieces to test my values. And again, this doesn't have to be perfect, just put them in order. So the negative 7 is to the left of 1. And now we can start picking values in each piece. So my favorite number that's less than negative 7 is negative 11. My favorite number that's between negative 7 and 1 right now is 0. And my favorite number that's greater than 1 right now is going to be x equals 2. And then I'm going to test each of these values in my inequality. I didn't have any simplifying, so I got one inequality. I'm going to plug them in there. So negative 11, I'm going to plug it in everywhere for x. Top and bottom, plug it in everywhere. So I'm going to have negative 11 minus 1 on top and negative 11 plus 7 on the bottom. My inequality says that should be greater than 0. So now let's see if this thing is true. I'm going to have negative 12 on top and a negative 4 on the bottom. That simplifies to 3. 3 is greater than 0, which means this works. So I'm going to include the part that's less than 7, negative 7, sorry. And so now let's test the other pieces. If I take 0 and plug it in, I get 0 minus 1 over 0 plus 7. My inequality says that should be greater than 0. I get negative 1 divided by 7, but negative 1/7 is definitely less than 0. This is not true, which means this part does not work. And then the last one here, x equals 2. I'm going to plug that in and get 2 minus 1 on top, 2 plus 7 on the bottom. My inequality says that should be greater than 0. 2 minus 1 is 1. 2 plus 7 is 9. 1/9 is in fact greater than 0, which means this piece works. And so now I'm just going to write my solution, just like always, in interval notation. So that means that this piece from negative 7 over works. So I'm going to go from negative infinity up to negative 7. Now, am I going to include negative 7? Well, my inequality says that I'm not going to include any of my endpoints, but also notice that because x plus 7 is in a denominator here, we know that x cannot be equal to 7 by the domain rule. So this is not going to be included regardless of what my inequality says. So negative 7 is definitely not included. And then I'm going to union that with this piece over here that works, which is everything bigger than 1. So I'm going to go from 1 to infinity. And I'm not going to include 1 because, again, my inequality says not to. So that's going to be a parenthesis over there as well. And that is the solution to this thing. All right, let's try another one. Number 2. X plus 6 over x plus 1 is less than or equal to 2. All right, well, again, I have to get my magical setup before I can start solving this. And this time I don't have a 0 on one side. That means I'm going to subtract this 2 over to the other side just because we could really move everything to either side, but I'd rather subtract 2 than subtract this lovely fraction. So I'm just going to subtract 2 from both sides so that I get a 0 over here. So I'm going to have x plus 6 over x plus 1 minus 2 is less than or equal to 0. Okay, I have my 0 over here. That makes me happy. But I don't have just one thing over here. I need to combine these into a single fraction. Technically, 2 is its own fraction because I can write 2 as 2 over 1. I basically need to have one fraction completely alone on the side that's not 0. We got to combine these guys. So to combine these guys, I need a common denominator. The common denominator over here is x plus 1. And so this guy already has it, so I'm just going to go ahead and leave that here. To get a common denominator here with this 2, I'm going to multiply the top by x plus 1 and the bottom by x plus 1 because that's what I need to get a common denominator. And so I'm going to have 2 times x plus 1 on the top and x plus 1 on the bottom. And that's going to be less than or equal to 0. So now that I combine these, I'm going to get x plus 6 minus 2x minus 2. So I distributed the 2 and I distributed this negative. So it's minus 2x minus 2 all over my common denominator of x plus 1. Now I can combine like terms. X minus 2x is negative 1x, and positive 6 minus 2 is positive 4, all over x plus 1, and my inequality says that should be less than or equal to 0. Okay, now that we've done all of that, we have our magical setup. I have a single fraction on one side and a 0 on the other. This makes me happy. I can go ahead and solve this. So I'm going to set the top equal to 0, and I'm going to set the bottom equal to 0. And so when I set the top equal to 0, negative x plus 4 equals 0, which means x equals 4. And when I set the bottom equal to 0, x plus 1 equals 0 means that x equals negative 1. So I have two solutions. I'm going to put those on my number line. Negative 1 is over here, 4 is over here, and I'm going to test values. My favorite number that's less than 1 right now is a negative 3. My favorite number between negative 1 and 4 is still 0. And my favorite number bigger than 4 right now is x equals 6. And so now let's test this. Again, you can plug them into any of these that you like. I'm going to plug it into this most simplified form down here. But you can plug them into your original. You can plug them in anywhere that you want. Just if you use your original, you're going to have to put it in a calculator, and you're going to have to compare whatever you get out on this side to 2. I'm just going to use this one because I would rather compare what comes out of my fraction to 0 rather than to 2. It's going to be better for my brain. So I'm going to take negative 3 and plug it in for x everywhere over here. And I'm going to get negative 1 times negative 3 plus 4 over negative 3 plus 1. And my inequality says that should be less than or equal to 0. So on top, I get 3 plus 4. And on the bottom, I get negative 3 plus 1, which is negative 2. And this is 7 divided by negative 2. That's negative 3.5. That is, in fact, less than 0. This part works. We'll do the same thing and test with 0. So when I plug 0 in, I get 0 plus 4 on top and 0 plus 1 on the bottom. My inequality says that should be less than or equal to 0. 4 over 1 is 4. That's not less than 0. And so this part does not work. And then when I plug in x equals 6, I get negative 1 times 6 plus 4 all over 6 plus 1. And my inequality says that should be less than or equal to 0. So I get negative 6 plus 4 over 7 should be less than or equal to 0. Negative 2 divided by 7 is less than or equal to 0. That's negative, which means that this part works as well. So now let's write our solution to this. Okay, so this part here works and this part here works. So I know I'm going to go from negative infinity to -1, and I'm going to union that with 4 to infinity. Okay, now whether to include the -1 and 4, we have to be extra careful about this. Our inequality symbol says, yes, there's an equal sign here. This says we should include them, right? Yes, we should include them. Except we have to be careful with our domain. The domain down here says that x plus 1 cannot be equal to 0, which means x cannot be equal to -1. So I don't care what my inequality says. I cannot let x equal -1 because I would really love for my brain not to explode. And so I cannot include -1. That inequality sign be darned. I cannot include it. So we're not going to include the -1 because it's in the denominator. But the 4 I can include because of this little negative, which means I am including it. And that is the solution to this thing. So be very careful with your brackets and your parentheses in here. Let your inequality symbol drive your brackets or your parentheses as usual, except make sure that you never include any x values that came from the denominator because our domain rule says that we can't do that. Okay, I want to do one more of these and then we'll call that good for homework 10. So number 4 is the one of these that I want to do just to kind of help you remember how to add and subtract fractions. Because we're synthesizing everything that we used in homework 9, and now we're throwing them together with inequalities. So all of this common denominator stuff and the domain rules, this is all coming from homework 9. We're reusing it, and we're reusing it in the background of another problem. So that makes it a little harder. But we've got this. We can do hard things. Okay, so number 4, x minus 1 over x plus 6 is greater than or equal to x minus x minus 2 over x plus 4. All right, the first thing that we need to do is get a 0 on one side or the other. We can really pick whichever one we want here. I generally like to put everything on the left and have the 0 on the other side. That's kind of how I'm programmed. So I'm going to subtract x minus 2 over x plus 4 from both sides. When I do that, these guys are going to cancel, and I'm going to get a 0 over here. And then over here, I'm going to get x minus 1 over x plus 6 minus x minus 2 over x plus 4. And my inequality symbol stays the same because I just subtracted something from both sides. Okay, now we need to combine these fractions so that I only have a single fraction over here, which means to subtract fractions, we need a common denominator. Okay, we love common denominators. So what is our common denominator here? Well, we need to run through our grocery list here and add anything that appears in any denominator. So from this first fraction, I need to add an x plus 6 to my list to make sure I get one of those. And that's the only thing there, so I'm going to move to my next fraction. And I also need an x plus 4 here. So that's not already on the list, so I'm going to add it. And that's all my fractions. So this is my whole list. This is my common denominator. And so now we do need, I know that we have an inequality here, and so we usually replace that with an equal sign. And I know that when we were solving equations, I told you to clear the fractions and multiply by your common denominator. But we need that denominator to break up our number line. So we can't just multiply both sides by our common denominator and clear the fractions. We need that denominator to put those solutions on our number line. So we're going to do Halloween costume time, and we're going to get equivalent fractions here with my common denominator of x plus 6 times x plus 4. Okay, so how to do this again? From here, we're going to let the denominators lead the way. What am I missing from this denominator to get to my common denominator? Well, we're missing x plus 4, so I'm going to multiply that on top and bottom here. And so then here I'm going to get x plus 4 times x minus 1. And then over here, what do I need to multiply by to get to my common denominator from where I'm at? This one's missing an x plus 6, so I'm going to multiply top and bottom here by x plus 6. And so when I multiply, I get x minus 2 times x plus 6 up here, and my common denominator on the bottom. Okay, everybody's got Halloween costumes on. They look exactly the way that I want them to with my common denominator, but there's still these same fractions underneath. And now I'm going to FOIL out each of these numerators so that I can combine like terms. Fight through it. This is going to be slightly annoying, but you can do this. So x plus 4 times x minus 1. We're going to distribute this x into the first and the outside. So it's going to be x squared minus 1x. Now I'm going to do my inside and my last. So I'm going to do plus 4x minus 4 up here. I still have my common denominator. Leave it factored. And now I'm going to FOIL over here. So I'm going to do my first and my outside. So I'll do x squared plus 6x. And now I'm going to do my inside and my last. And I'll have minus 2x minus 12, keeping that common denominator. Okay. Now I can combine things here. So over here, I've got negative 1x and a plus 4x. I'm going to have x squared plus 3x minus 4. And are you okay? I'm going to combine these into one fraction as well. So I'm going to subtract my numerators here too. So this is this first numerator, and I'm going to subtract the second one. And while I do that, I will combine my like terms here. Plus 6x minus 2x is plus 4x. And then minus 12 all over my common denominator of x plus 6 times x plus 4. Okay. And then don't forget to distribute this negative. And so we are going to have x squared plus 3x minus 4 minus x squared minus 4x plus 12 all over my beautiful common denominator is greater than or equal to 0. These x squareds cancel. 3x minus 4x is negative 1x. Negative 4 plus 12 is plus 8. And on the bottom, I have x plus 6 times x plus 4. And that is going to be greater than or equal to 0. Okay, my friends, all of that work that we just did got us set up correctly. I have one fraction on one side, I have a 0 on the other. Now I am ready to set the top equal to 0 and the bottom equals 0 to get everything to put on my number line. So setting the top equal to 0 gives me negative x plus 8 equals 0, which means 8 is equal to x. And when I set the bottom equal to 0, I get x plus 6 equals 0, which means x equals negative 6. And x plus 4 equals 0, which means x equals negative 4. I'm going to put all of these guys on a number line. And again, it doesn't have to be perfect, but you just have to make sure that you kind of put them in order. So -6 goes furthest to the left. That +8 goes furthest to the right, and then the -4 is in the middle. Okay, and now we just have to test our values. If we cut this up at each one of these things, I've got 4 pieces to test. So I'll plug in x equals, I don't know, -10 over here. And I'll just go with -5 in here. And I love x equals 0. And how about x equals, I don't know, 13, just for funsies. Okay, and then the wild thing about this is that you can plug these test values into any one of these inequalities you like. This one, or this one if you're really feeling crazy, or this one. I mean, shoot, you could even put it into this one if you really want to, but I don't want to mess with all of those x's. Um, so really, I would advise you to either choose this guy or the original one. It's pretty much going to be kind of 6 of one, half dozen of the other. I'm going to plug it into this bottom one, again, just because my brain likes to compare to 0. If you plug it into this top one, you're going to have to plug in your x's, find a value here, find a value here, and then compare both of those numbers to each other to see if your inequality is true or false. But down here, I'm going to plug in my x value, calculate the value of one fraction, and compare it to 0, which is usually much easier for your brain to do. So I'm going to pick the one with a 0 in it. So when I plug -10 in, you get -1 times -10 plus 8 all over -10 plus 6 times -10 plus 4. And that's, my inequality says that should be greater than or equal to 0. We'll see if that's true or not. And then, so I'm going to get 10 plus 8 over -4 times -6. That says it should be greater than or equal to 0. I get 18 over 24, which if you take 18 divided by 24, I'm going to get a positive number out of that. So that is definitely going to be greater than or equal to 0. So that means this works. And then you can do the same with each of these. Just for the sake of time, I want to make sure that I kind of get through these and still not keep you over. So when I plugged in -5, I got that this one did not work. When I plugged in x equals 0, this guy did work. And my x equals 13, when I plugged it in, this did not work. So I'm going to throw out these two sections and I'm going to keep this section and this one. Okay, so now I'm going to write my solution. Now, my inequality was greater than or equal to, which means include your endpoints, except remember, whatever the inequality says, you cannot include anything from the domain rule. So because my domain rule, because I got this on the bottom, x cannot be -6 and x cannot be -4 because of my fraction domain rule, which says I cannot include either of these. But my inequality with this equal sign says that I will include 8. And so overall, I'm including this guy and this one, which means my solution here is going to be -infinity to -6, open because that's in the denominator. And I'm going to union that with everything from -4 to 8. I'm going to leave it open at -4 because that's in the denominator. And I'm going to close it at 8 because my inequality says to include that one. And that, my friends, is the solution to this inequality. So some of these get long, and I want you to fight through it. We're increasing your tolerance for annoying things, but you can absolutely do this. So hang in there, fight through it. Um, and that's homework 10. Hopefully, I'll be feeling better and I will see you on Wednesday. I hope you all have a safe and a happy Halloween. And I'll see you on Wednesday, which is going to be November, which is bonkers. So I'll see you in November, y'all.